All right, welcome to Lesson 8.2 Geometry Notes, Proving Triangles Similar, Proving Triangles Similarity by AA, SS, and SAS. So some of those maybe look familiar. We used some shortcuts to prove triangles were congruent, not necessarily similar. We just first look at similarity, but there's definitely a connection between some of these. This one's a little different. But that's kind of the gist of the lesson is how can I show specifically triangles are similar using a couple different shortcuts. So let's jump in. Let's get it going. Um, First one, let's start with AA, this new one, the angle similarity theorem. So pause this, add it to your notes. Basically what it says is we've got two triangles, that I'm maybe suspecting are similar or I'm being asked to prove are similar, not congruent, right? Totally different. I know they're going to be similar if two angles of one triangle are exactly identical congruent to two angles of the other triangle. Okay, that's enough. That's all it takes to know that those triangles would have to be similar. Okay. So that's what we're on the lookout for. So we'll look at here. I know proofs for a lot of us were something that we weren't the biggest fans of earlier on. We're still proving, right? That's the name of the lesson. We're not going to do two-column proofs, but I'll show you how we're going to do it in a few examples here. So we're already up to examples. That's awesome. We'll just focus one at a time here. So let's take a look. We've got, what are the directions asking us to do? Determine whether the triangles are similar. Explain how you know. If they are similar, write a similarity statement for the triangles. Okay? We can do that. So I look at the two clearly not congruent. Nothing's going to be congruent as far as the triangles. I'm looking at angles and I can see that, hey, there's a 90 and a 90 there. So I know for a fact, and I'm not going to ask you to justify that, but all right angles are congruent by the right angle by the right angle congruence theorem. But I see different numbers, 26 and 64. What I need to do for this particular problem, if I want to use, we're obviously coming right off that AA similarity theorem. I need to either show one way or another that yes, two of the angles of this triangle are the same as this one, or that they're not the same, that I don't have congruent angles. So I think I'll maybe just start with K here and just figure out, you know what? I know the triangle sum theorem tells me that all angles of the interior angles of any triangle has to add up to 180. So I can use my calculator to go 180 minus 90 minus 64 and say, hey, you know what? The measure of angle K equals 26 degrees. I could confirm, but I'd be willing to bet without punching a single thing on my calculator that angle E right there is 64 degrees. So what have I shown? What's the point here? Well, I already know that I've got right angle. That's one pair of angles congruent. We've just essentially shown angle C is congruent to angle K. They're both 26 degrees. So a little less formal than a two-column proof. The only thing I'd ask you to do is justify a little bit. It does say explain how we know. Where did this 26 come from? It's not magic. It didn't just show up. I used the triangle sum theorem to show that, okay, hey, I've got two pairs of, to come up with that 26 basically and match it with the other triangle. And then kind of by default, these other two, that's basically, that's how or why the AA similarity theorem exists, is that, well, if two pairs of angles are the same, we know the third pair would be the same. But anyways, I'm just kind of justifying within the problem on the actual figures themselves, where did this come from? I use the triangle sum theorem to come up with that 26. Now I'm going to say, to kind of wrap this up, are these similar? Yes, similar by the AA similarity theorem. We can abbreviate for sure. All right, so that's my explanation. I've justified the one pair of angles that I had to come up with. The last part it's asking us to do is, okay, if they are similar, which we said, yep, by the AA similarity theorem, they have to be, give me a similarity statement. So essentially just say it now that this triangle CDE, here's my symbol, is similar to triangle. Just line everything up. I started here with C, so I got to start down here with K. So K, I went to D, which was the right angle, so I got to move to the right angle. And then process of elimination, we got to finish with H and E. Okay, so that's the last part. That's my similarity statement for the triangles. Right. So could it be worse? Probably. The 2-column proof where I'm asking you to justify everything. Really, the only one thing to justify there was the triangle sum theorem is how we came up with that 26. All right, let's look at part B. Maybe you can even guess what's going on here. Just it's the same exact kind of process. I see two triangles, clearly not congruent. Are they similar? I don't know. I see a 21 and a 21. That's like given. That's like the old school given information. Let's look over here. It's the exact same type of setup where clearly 99 and 61 aren't the same. But I'm curious, what is the measure of angle y? The measure of angle y is going to be 180 minus 99 minus 21. My calculator says 60. 60 degrees. Oh my gosh, that's so close. 60 versus 61. Well, close doesn't cut it. So these triangles are absolutely not congruent. So y is not congruent to t. Therefore, there's no way that s could be congruent to z. So what we're going to say here, that's really kind of what I need to come up with. You could also, still justify this by saying the triangle sum theorem. Like, where did that 60 come from? It didn't just magically appear. We applied some knowledge that we knew. We know what the triangle sum theorem says. So let's say not similar. Sometimes we struggle with these ones that are not, though, as far as it's still asking us to, okay, hey, determine whether the triangles are similar. Explain how you know. How do I know they're not similar? How do I say that? So I would say, if I want to be concise and short about this, I would say I should say corresponding angles are not congruent. All right. And that's all it takes, basically. Like the AA similarity theorem doesn't apply because we don't have two pairs of congruent angles. They're not congruent. Okay. So that's one look kind of involving numbers. I got a second one set up here. It's a similar type of question. This is more, so let's pause, set it up, sketch it, add it to your notes, and then we'll go through the solution right now. This is more, hey, these two triangles are similar. It's telling us that they are similar, but then this is the explain, how do you know? So it's kind of it's related to the last one, except there's not, we know there's not going to be a no. So let's take a look here. Again, let's just kind of maybe focus on this first one. Get enough room to write. How about that? Okay. So what do I know? This is all I know. Holy cow, that these, it's kind of like the given information. EB is parallel to DC, those two segments. Great. Awesome. I think the first thing that, at least on one like this, is to focus on where are these two triangles. We're talking about triangle ABE, which is this triangle. I'm just going to re-highlight my parallel marking there. And then we're also talking about triangle ACD, this bigger triangle. How are those the same? So there's different ways to kind of go about this. I clearly see the 52 in this triangle for angle ABE. And I'm thinking, you know what? Based on previous lessons, previous chapters, when parallel lines, this angle right here needs to be congruent to that angle right there. So we should say something along the lines that angle ABE, ABE, and I've marked it. So you could do something like this too, is congruent. Those are congruent to angle, just C if you wanted to say angle C. Those are congruent by, this was just supposed to be me writing arrows right there. So if that confused you, my apologies. What would be my reasoning? Either way, whether I write it out like this or kind of just do like the arrow thing and say like that angle and that angle are congruent, my explanation should be the C corresponding angle postulate, right? So that's going back to parallel lines. I've got two angles in the same position in relationship to their transversal and parallel line, upper left. Those are congruent by the CA postulate. Awesome. That's one pair. You could make that exact same argument over here. So let's change color here maybe and go with this angle pair right there and right there. So again, we could write it out as angle AEB being congruent to angle D by the exact same reason, CA postulate. I'm going to actually put a third one on here, even though at this point we could totally say these two triangles are similar by the AA similarity theorem. I want to at least mention angle A because I think a lot of people see that up there, that these two triangles, they're overlapping with this angle A. So they're sharing angle A. So it's going back, again, a little ways when we use this same reason when we did triangle congruent proofs. But angle A is congruent to angle A. Why? How do I know that? That an angle is congruent to itself? That was, remember, called the reflexive. Oh, yeah, we did it with sides a lot. Property of congruence, right? We saw it a lot with triangles, two triangles that were maybe sharing a side like that. And we said, hey, this side is congruent to this side because they're sharing it. And that's the reflexive property of congruence. We're seeing it here with angles, okay? So I'm not trying to confuse anybody. That's something that's probably going to come up throughout this section. That's one way that we could get angles congruent, the reflexive property, or the CA postulate. So at this point, explain how you know these two triangles are similar. I'm justifying all this stuff. I've got a reflexive property saying A is congruent to A. I've used a CA postulate to say angle ABE is congruent to ACD. We've met the criteria, actually overdid it for the criteria of that AA shortcut. So I'm going to say triangles are congruent, or I'm not congruent. I'm talking silly here. Similar by the AA similarity theorem. Okay. And right now, obviously, we've only learned the AA similarity theorem. So it seems like, oh, of course, that's AA. Just be aware, obviously, there's an SSS and an SAS similarity theorem that we'll add as well. So the proofs could be similar. Just we could get side length information. Okay. Let's look at the second one. So it's definitely, it's not a repeat, new concept here. We've seen kind of figures like this, except again, these are not congruent. We're told, or basically not told, but explain how do we know that these two triangles must be similar. So I'm going to go on ones that we haven't seen yet. I'm going to mark this angle right here congruent to this angle. This is going back to maybe even chapter 1. That angle SVR has to be congruent to angle TVU, and I'm fine with doing this. You know, I guess it's easy to tell in mine with the color that those two angles, SVR and TVU, have to be congruent because of the vertical angle theorem. Sweet. That's awesome. That's only one pair, though. I can't say, oh, these got to be similar because of the AA. That's only one pair of A's. I need a second pair. Again, they're not, just like the last one, they're not giving me this parallel just for fun. It's there because it's expecting us to use some of that parallel line, those parallel line proofs or parallel line theorems from chapter 3. I'm going to go here with angle S being congruent to angle U. And as long as I can come up with those names, we would say something like angle, let's see, angle S. So this is if you're just working in like pencil or whatever, and it's hard for me to kind of distinguish, I need to see a little bit of what you're saying there. How do I know angle S has to be congruent to angle U? Because of the alternate interior angle theorem. That's the name of that pair. Those are congruent, and now we've met our criteria. I've got two pairs of angles congruent, identical. Now we can say the triangles must be similar. It's actually the exact same. Similar by the AA similarity theorem. All right. So a couple good looks for us. I like those. Just it's good to review some of that stuff as far as reflexive property of congruence. We've used these a little bit too, even with some of the current chapters. I know in quadrilaterals with diagonals, there was alternate interior angles with parallelograms. Not as much corresponding angle postulate, but even vertical came up a little bit when our diagonals intersected in quadrilaterals. So hopefully the stuff isn't going too deep for you. We haven't been away from it from that long. So just a couple examples of how we might prove, right? That was one of the lessons, prove triangles similar. That's all using the AA similarity theorem. Let's crank out these other two here because they kind of go hand in hand. The side similarity theorem. So what that says is basically I've got two triangles. If their corresponding side lengths are proportional, right? And essentially we're meeting our criteria of what does it mean for polygons to be similar? Their angles have to be congruent and their side lengths have to be proportional. Okay. Now we're taking some liberties. We're saying I don't need to know anything about the angles here because these are triangles, and how this works is all I need to know is that the side lengths are proportional. So basically, if I take AB and divide it by RS, and AC divided by RT, and BC divided by ST, and I get the same value, those are all equal ratios, the two triangles must be similar. So this one's tougher to do as far as, tougher in the sense that there's not a whole lot of ways to show this other than knowing values here and here, or for all three of these side lengths. So that's kind of where these are differ a little bit, the proof portion of it. SAS, let's get this one done. The SAS similarity theorem, very similar. It's kind of a hybrid of the last two. Okay, so on my picture here, however we come to this information, angle X is exactly congruent to angle M. Great. But maybe that's all we're able to know. We don't know anything about these other two angles. I can't use the AA similarity theorem. But however, we come to the information that if I take ZX and put it over PM and XY and put it over MN, those ratios are the same. That's kind of my SAS configuration that we saw with congruence. SAS congruence, where the included, so there's the word there. Whoops, didn't mean to write over the top of it. Including these angles, the triangles would have to be similar. So we'll look at, actually these last two examples both involve the SSS similarity theorem. But hopefully we can extrapolate, how this would fit, kind of like I said, a hybrid of some of these concepts with CA postulate, reflexive, and then maybe knowing some side lengths that fit those in there. So let's take a look. All right, actually, this is it, our last two examples. So what's it's asking us here, we're kind of giving us like a model and saying, all right, here's triangle ABC. Is either this triangle or this triangle similar to ABC? And again, be sure to justify your answer. I think we can justify it with numbers, and we'll have just like a follow-up explanation. So what I'd be looking to do, let's see if we can color code this. AB. Who would AB's partner on this triangle be? AB has to partner with DE. So if I take 8 and partner it with the 6, if these triangles truly are similar, that should divide out to be the exact same value as us taking BC, which BC's partner would be EF. Where's EF? Right here. So taking the 12 and putting it over the 9, which needs to be exactly the same as us taking CA. And CA is the first and last, and putting that over FD, which, I almost wrote FD. FD is 12. Do those all simplify to the same? So I see it, if I just want to keep fractions, all three of these fractions reduce to 4/3. So that would be my scale factor. And the fact that, really mainly the fact that this is true, that they all equal the same value. You could divide them out, you could calculators and say 1.333333 repeating. But this is 1.333, this is 1.333, this is 1.333. We're good. This triangle, let's say it. Let's kind of make that statement. Triangle DEF is similar to triangle ABC by the SSS similarity theorem. And I'm totally fine with that. We've justified it. Everything's backed up there. Those all work out. Mine's beautiful, color coded and everything. So kind of like our first example, let's take a look at, I'm guessing, Mr. Crow's probably going to set the second one up where it's a knot. So I can kind of see by the shape that, something's up here. What's going on? Let's try to stick with the same colors here and see if we can figure this out. All right. I'm actually going to start with this one here, that AC. How long is AC? AC is 16. AC's partner on this triangle over here needs to be GJ. So where's GJ? Right here. So there's a 16 to 16 ratio, or that one's easy to tell. 16 to 16 reduces to 1. There's a 1-to-1 ratio on this side length. So everything else needs to have a 1-to-1 ratio, and I can already tell. We got to be careful a little bit. Let's go to the AB here. AB, that's 8. Okay. 8. AB is red. The first 2 letters listed needs to partner with GH. Where's GH? Wow, look at that. GH is 8. So there is, so far so good, an 8-to-8 ratio, a 1-to-1 ratio. The one that I think is going to get us here is our BC. So BC is 12, and I can, everyone's screaming at the computer right now. Clearly, BC needs to partner with HJ, which HJ is 10, and we lose that 1-to-1 ratio. So this is the one that, no good. These would not be similar. So let's say it just like before. There's still that element of, so what? Yeah, what does this work mean for me? Explain it to somebody that maybe doesn't understand. Let's just say the triangles are not similar. Why not? How do you know? Because corresponding side lengths, corresponding side lengths are not proportional. So it has a very similar feel to things that we did in the previous lesson, where you're kind of confirming one way or another, yes, these things are similar, or no, they're not. The only difference between this one and the last one is we don't have to look anything with the angles, right? The other one, in 8.1, we looked at, well, you got to see the angles are all congruent, and then you got to show that all the sides are proportional, all the corresponding sides, where with these shortcuts, we don't have to necessarily know anything about the angles. Okay. Justified, awesome, everything's explained. Look at those pretty colors. All right, one more to go here. Find the value of x that makes ABC similar to DEF. Okay, so they look about the same shape, just one's shrunken down. There's different approaches here. I'm going to stick with the proportions. So let's take a look here. That what needs to be true? Well, we just looked at it. If these are truly going to be similar, this BA side 4 has to partner up with this side the same way that this BC side, which is x minus 1, is going to partner with this side. Let's just start with that one. That has to be a true, if these are going to be similar, that needs to be true. So I basically get the option to let's make this true. What value of x is going to make this true? I'm going to show a cross multiply here. We didn't see one in the previous lesson. Maybe this. Well, with this going on with this x minus 1. So on my first cross multiply, no problem. 4 times 18. My cross products is one of them is 72. And then on the second one, when I go this way, just be careful. There's like an imaginary parentheses there. This is really 12 times x minus 1, that whole quantity. The common mistake would be to leave the parentheses out, and then you just do 12x minus 1, when it really should be, if I distribute here, 12x minus 12. We can solve for x, and I think we'll be all right. So add 12 to both sides. I'm just kind of getting tight on space here, so we'll go 84. I've added 12 to both sides, and then we'll divide by 12 to get x equals 7. So I like that x value. I think that's okay. The kind of cool part here is that there's a couple different x's. What I would maybe look at doing is just sketching. So my show the work, my justify here might be something that almost just re-putting them back together with that x value in there, just to confirm everything that we think we're good with. So this would be 4. Now if I plug the 7 in there, 7 minus 1 is 6, and then 8. And then on this bigger triangle DEF, doesn't have to be perfect. I think I got the 12 here. Well, let's label DEF. On this triangle here, I already know the 12. I already know the 18. Whoops, that's 18. And 3 times, let's see, 7 plus 1 is 8. 8 times 3 is 24. Are all these the same? Let's see. 4 over 12 is the same thing as 6 over 18, which hopefully, if we've done everything what we're supposed to do, AC 8 over 24, those all simplify to 1 to 3. So absolutely, these triangles truly are similar when x equals 7. That's kind of one of the values we need to see, x equals 7. How are they? How do I know they're similar? The SSS similarity theorem says so. All right. So again, another just different look there that we're seeing. All right. I think that's it. Yeah, no reason to make it longer. Obviously, like I said, the proof type of ones we could get side length information that would just add, make these more into an SSS or an SAS type of problem. But I think you guys can handle that. All right. So that's it. We've used all three in a couple different looks, showing that triangles are similar, essentially proving triangles are similar. That's it. Let's call it lesson 8.2 in the books. I'll see you in future lessons.